istables now. Why do we even need an istable? You need an istable to find the concentrations at equilibrium. You know, when you have Kc or Kp, you plug in the values that are at equilibrium. But in this question, we have Kc, but we don't have the concentrations at equilibrium. We have the initial concentrations though. So we'll see how to make an istable first. We have I's. So I over here stands for initial, so initial pressure and initial concentration. This is the change, and E is equilibrium, so concentration at equilibrium, pressure at equilibrium. Over here, although it's concentration because it's Kc. So for starters, to make it easy for us, we can just write the equation on top here. So if you see, the equation is already balanced, so the moles here are like 1, 1, and 1. So you don't need to balance it because it's already balanced. So initially we have 1.50 molar of carbon dioxide, 1.1 for H2. So because it's initial, so in initial you don't have the reaction even started yet. So obviously you're gonna have 0 products. So yeah, that's self-explanatory. Now when it comes to change, you're using your reactants. So this is going to be negative x, this is going to be negative x. X is the change because we don't know how much is getting used up for us to reach equilibrium, so we just call it x. But we know that it's getting used up because it's a reactant, so we put a minus. And similarly, if your products are going to get made, so you put it positive x and positive x. Now it could be negative 2x, or negative 3x, but over here it's negative 1x. But how do I know all of them are negative or positive 1, 1, 1, 1, 1? That's because of the moles that I have available. So let's say, for example, I had 2 carbon dioxide moles. So I would put a 2 over here. Let's say I had 2 moles of H2O. So I would say plus 2x, but I don't, so I'm just gonna write it as 1, 1, 1. So because of that, I'll just say 1, 1, 1, 1 to make it more easy, or to make it understandable. And then at equilibrium, we'll just combine them together. So over here, I'll have 1.5 minus x, and then 1.1 minus x. And this would be 0 plus x, so this is just x, this is just x, plus x plus x. Now I can write my Kc. How do I write my Kc? Products over reactants. So products are H2O, carbon monoxide, H2, and carbon dioxide. So over here for Kc, because I need to write the equilibrium values over here. So what do I have for equilibrium using my istable? For my H2 and O2, I got x times x, well, which is also x squared, but let's just go with it for now. And I have 1.5 minus x and 1.1 minus x. I have my Kc value, which is 9.71 times 10 raised to the power negative 6. Now I could write it as this and solve for x. But what do I see here is that when I need to find it for x, I would need to make it in a quadratic equation. How do I know that? It's because if I shift it here, I shift all of it over here, equals x squared. These two are gonna get multiplied and make an x squared, so it's gonna be a quadratic equation. I need to put a quadratic formula here, but that's gonna be a long way. So to make it easy for me, I'll use small x approximation. Now how do you do small x approximation, and when do you do small x approximation? So for small x approximation, whenever the value for Kc or Kp is less than anything that's 10 raised to the power negative 5. So if you have anything that's equal or less than -5, then you use KC, then you use smallest approximation. So over here, the value I have for my KC, which is raised to power -6, which is smaller than -5, so that means that I can use small x approximation. Small x approximation would basically mean that the value I'm gonna get for x is really small, to the point that it's quite negligible. So how do I put it? So I'll start with this step right here that I did. So I'll say 9.71 times 10 raised to the power -6 x squared, and the x's I have over here, I'll just ditch them, because the value, whatever value I'm gonna get for x, is gonna be so small that when I subtract it from 1.5, it's not gonna make a big difference. It's gonna be really minute, so I can just drop it all together, because my KC is -6, is 10 raised to the power -6. If it was 10 raised to the power +6, I cannot use small x approximation. That I would need to go the long way, which is the using the quadratic formula and finding the value for x. But here I can, and now I'll just solve it using maths. 1.5 1.1 equals x squared. Well, I can just straight up say that I can just take x squared, and I think I'll get 10 raised to the power -3 as x. So if I look at my table here, my x is my change, so I can say that this is my change. But what is that my question was asking? My question is, what is the concentration of all the reagent once equilibrium has been established? So once equilibrium has been established, so I need to look at all of these. So how much of carbon dioxide I have, how much of H2 do I have, how much of carbon monoxide I have, or water I have. So if I look at carbon monoxide and water, they both are x, so that means that I have 4 times 10 raised to the power -3 of H2O concentration, and I also have that much of carbon monoxide. But for my carbon dioxide, because it's 1.5 minus x, so I'll do 1.5 minus x, which is this. Whatever I'm gonna get is gonna be so small that it's quite equal to being 1.5. And similarly for H2, which is 1.1 minus 4 times 3, and whatever value I'm gonna get is gonna be quite near to 1.1, so I can just, so 4 times 10 to the power -3 is not creating much of a difference. So these are my values at equilibrium.